All right. Okay. Welcome, everyone. Thank you for coming for this very distinguished seminar. It's a pleasure to have here today Dr. Kerkil Choi, who's a research scientist at Duke University. Dr. Choi got his BS degree from Inha University in South Korea, and he got his MS from University of Florida, and his PhD from Georgia Tech, and in 2005. And he's been also a postdoc at Michigan Tech University, working with Dr. Schultz, and more recently, since 2008 to be precise, he's been at Duke University working with David Brady on imaging and spectroscopy. It's a pleasure to have you here. We'll be talking about some of his recent research. Thank you for coming.
Thank you very much for the nice introduction. Again, my name is Kerkil Choi. I'm a research scientist at Duke University. I noticed my talk is right at 1 o'clock, so it's right after lunch, so I make sure people don't fall asleep. Actually, my presentation materials have gone through a lot of changes for the last couple of days. I'm mathematically very oriented, so I used to have a lot of equations and things like that, and I did practice with my students, and like every single one of them complained about it's unfriendly, although I said it's friendly, so I make sure it's friendly. And this talk is specifically designed for those of you who don't have much background in mathematics, but this designs to get you interested in what computational sensing does and how you can use mathematics in the real practical problems. So let me learn a little bit about my audience. How many of you have taken linear algebra? Okay, that's good. Probability? How many of you have heard about compressive sensing, like recently emerging theory of signal processing? Few? Okay, that's fine. So, all right. So I would like to introduce you to the concept of compressive imaging, which is a sub-area of fantastic, interesting area of computational imaging. And especially, I would like to demonstrate the plausibility and the efficacy of the method using an instrument that has been developed in our group at Duke University, which is coded aperture snapshot spectral imaging system. Conventionally, imaging involves taking a picture of an object of interest on a pixel by pixel basis. Do I have laser pointer somewhere?
Unfortunately.
Yeah, I can use my hand. Okay.
Yeah. Just your pointer there, your
sure. Okay. So imaging takes, imaging involves taking a picture of an object of interest on a pixel by pixel basis using a camera. However, in many situations, the object of interest is not directly observable. For example, it is not possible to see inside of your body directly unless you undergo a CAT scan. In fact, computer-aided tomography is a cool application of computational imaging sensors where the computation is essential to recover the image of the object of interest. The environment is very interesting. It keeps me nervous. Yeah. So in many applications, including tomography, the problem of recovering the object of interest F from the sensor data G can be modeled by this linear system of equations. And in this equation, the effect of the system is modeled by this matrix H. Of course, in reality, the sensor data is always corrupted by noise, so you have to add noise term to make your model more realistic. So when you design H, of course, we want to design H such that the recovered object F satisfies a certain set of criteria. For example, you want your recovered object to be highly accurate and have high signal-to-noise ratio. In addition to these mathematical considerations, of course, in reality, the design of H should also consider physical constraints. For instance, this 2D bird image is some type of projection of three-dimensional scene structure. But if you are interested in scene structure, this 2D image may not contain enough information or may not have an enough number of measurements to set up a nice equation G equal to HF that you can stably invertible, which means H is square matrix. So you have, in such a case, you have an underdetermined system of equation. So to give you an idea of what the problem is with underdetermined system of equation, let's consider a case where your H matrix takes some of a set of 4 elements in this vector F. Then, as you can see, you can replace this set of 4 measurements, or no, sorry, set of 4 numbers. You can replace this set of 4 numbers by any permutation of those 4 without changing these measurements. So all those numbers are basically candidate for your solution. So you have non-uniqueness problem of the solution. Compressive sensing is a fascinating, to me, fascinating emerging concept of signal processing. Yeah, it keeps me nervous again. It's a fascinating emerging signal processing concept that provides us a solution to such an underdetermined system of equation for sparse F, which means you only have a small number of non-zeros in your F. So to get an idea of what that means and how sparsity can be exploited, let's consider this example again, where your F is assumed to have only 4 non-zeros. Then, because you all have linear algebra background, I would just skip explaining the details. But this matrix equation is basically equivalent to this matrix equation, which is fully determined that you can stably inverse to find the solution back. So now a very important question is, we don't know what F is, and we don't know how many non-zeros we have, things like that. So the question is, how can we make this happen for every sparse vector F with certain sparsity? There are 2 keys for compressive sensing to work. The first key is that you want to design this H matrix or your physical system such that every submatrix, such as this matrix, every submatrix corresponding to any sparse vector F with certain sparsity, becomes stably invertible. And then once you have such a physical system, because your G contains all the necessary information, basically meaning that you don't lose any information, you need a nice solution approach to retrieve this F back from this data G produced by this H that satisfies the first key. So the first key concept, the first essential key concept is formally stated as this inequality called the restricted isometry property. What this property tells us that if your H matrix, if your physical system preserves the length of every possible sparse vector F sub S, then you're guaranteed to have non-uniqueness of solutions when you solve this underdetermined system of equation G equal to HF. Pretty interesting, huh? So to understand how this inequality can give us the uniqueness of solutions, let's consider a case where your system matrix H satisfies this inequality for any 2s sparse vector F. And also assume that you are given an arbitrary 2s sparse vector f, then that 2s sparse vector f can be represented as a subtraction or addition of two non-overlapping s sparse vectors. And this subtraction of those two s sparse vectors can only be mapped to 0 vector by this matrix H if and only if this vector itself was a 0 vector. Because this H satisfies that it preserves the length. So what this tells us, what it implies in practice is your sensor outputs, two outputs, cannot be the same unless you really have the same inputs. So that guarantees you the uniqueness of solution because you have every different input, you have every different output. So now the important question is, then it seems like it's a very intimidating inequality. People seem to have trouble understanding what that means. Yeah, I have my own understanding, but I'm not sure that's really perfectly reasonable thing. But the question is there any such matrix that satisfies this intimidating inequality? As it turns out, there are several matrices that are well known to satisfy this nice property. For example, if your matrix is composed of elements that are generated according to some random distributions such as Gaussian or Bernoulli, and if the matrix, the number of rows of the matrix is order of the sparsity, the number of non-zeros in the vector f times log of the length of the vector, then it's guaranteed that with very high probability your matrix satisfies the restricted isometry property. Well, of course, in practice, it's difficult to make every possible element of your H matrix to be purely random as you want. Yeah, it's some random, but you want some randomness as you design. So it's kind of tough. Another class of such a matrix that satisfies restricted isometry property is called incoherent measurement matrix. This is just basically, again, because you all have linear algebra background, this basically means your matrix is composed of a random set of rows taken from a unitary, for example, Fourier transform matrix, or an orthogonal matrix, such as Hadamard matrix. So as in this example, if your matrix is composed of these 5 rows, then with very high probability, it also satisfies the restricted isometry property. So this is very important in many applications because, for example, MRI. MRI can take random Fourier samples based on the sensor positions. In fact, compressive sensing was developed in the field of MRI imaging in the first place, involving very smart mathematicians. So now the second important key concept is, okay, now we know how to make the H matrix. Okay, let's say our H matrix or a physical system happens to satisfy the happy restricted isometry property. Then, well, how can you find the solution then? It turns out that you can find the solution by searching through all the possible solutions that satisfy that underdetermined system of equation G equal to HF and pick the sparsest one among all those possible vectors. Maybe there are infinite number of possible solutions. It turned out that it is a unique solution and the correct solution to that underdetermined system. But this approach is, which is called L0 minimization, is very impractical because it poses a combinatorial NP-hard problem. So you have to search through all the possible solutions that will take forever. To my perspective, the most beautiful result of compressive sensing is that if your matrix satisfies the restricted isometry property, then rather than solving this L0 minimization problem, you can actually solve L1 minimization problem, which is a convex problem. And what's beautiful about that? This will produce exactly the same solution to that problem if your matrix satisfies the restricted isometry property. And that's very important because this is a convex problem, so you can find the solution in a finite time in a very stable, efficient way. So to get a little taste on why that L1 minimization has to work and how L1 minimization finds the sparsest and the correct unique solution. So in these graphs, it's hard to see. Can you see the hyperplanes? It's much easier to see the vector. So these hyperplanes, 3 hyperplanes, represent a set of all possible solutions to this underdetermined system of equations. Of course, in 3D, poses line or a plane. And these 3 balls represent L1 hyperballs, meaning that your F satisfies, your L1 norm of the ball is equal to some constant. To remind you of what L1 ball is, this is the definition of L1 norm. So it looks like a diamond in 2D. In 3D, it's some sort of L1 ball. Yeah, I'm repeating myself. So let's consider these 3 graphs to understand how they can find a unique, correct solution. So suppose you have hyperplane and L1 ball which does not touch this hyperplane. Then the F on this hyperplane, F on this L1 ball, although it's sparsest among all F's on this hyperballs, because this does not touch this hyperplane, this does not satisfy the linear system of equations. On the other hand, if you have L1 ball intersecting the hyperplane at an infinite number of places, all possible F here satisfy both the underdetermined system of equations and this ball equation. However, these solutions are not sparser than the solution defined here. So this is exactly what your L1 minimization finds. As you can see, once the ball touches, there's only single point that is sparse, and that satisfies this underdetermined system of equation. So that will guarantee you the uniqueness of solution, and that's, in fact, a correct solution. So this is the most important result of compressive sensing. So I would like to make this more interactive than just being a monologue. So I'm very excited about giving a talk, but if you have any questions, just feel free to interrupt me anytime, and feel free to ask me questions. So now you can ask me or someone else a very important question. What if F is not sparse? We're only talking about sparse F. So what if your vector contains, or it's just full of many non-zero elements? Then it turned out that you can use some sort of transformation, to transform that non-sparse vector F to some sparse vector F. That is the idea of data compression, basically. So suppose if you have a natural image, you can use wavelet transform to make it sparse or compressible. It's basically the idea of, in this graphical interpretation, you rotate this non-sparse vector using some rotational transformation to put that on one of these axes. So those vectors on the axis will automatically be sparse vectors. Well, of course, the important research is, how can you find the nice transformation that can map this vector to one of those sparsest vector. So that composes a huge field in compressive sensing too. So with this theoretical framework, we can apply compressive sensing theory to many physical important applications. One such an application is hyperspectral imaging, or spectral imaging that I'm going to talk about now. So spectral imaging aims to find the 3D data cube information consisting of spectrum of light at each spatial location of the 2D scene. Why spectral imaging is important? Spectral imaging, because it finds unique spectrum at each spatial location, it may be used to identify some material or some objects, or even it can be used for astronomical imaging or biological clinical study for detecting disease and understanding some biomaterials moving around. This is an example of spectral imaging of fluorescent beads, taken by an instrument that has been developed in our group. So when it's moving, we keep track of where it's going. So understand how your biomaterial is moving around in your body. So the main problem in spectral imaging is that your monochromatic sensor array integrates this 3D data cube along the spectral sensor array, which implies your linear system of equations is highly underdetermined, especially when you have so many spectral channels. One approach to solve that underdetermined system of equation, or basically do spectral imaging, is to use color filter array. As you might all know, this place loves me, right? So as in this example, you have RGB color filter array. But this color filter array approaches have many drawbacks. One example is because it divides the detector area into many different colors, it suffers from a loss of resolution. And also, because you block the signal using the filter, the signal that you want, other than the signal that you want to get, you have necessarily a very low SNR because you block the signal. Another important problem is, as you see in this pattern, because every color filter array captures different portion of the spatial scene, there's spatial inconsistency. It's called mosaic problem. So when you put together these images, they're not exactly the same. So you have to use interpolation or some other approach to make it looking really nice. It's been researched by many smart researchers in various different fields. And of course, all these problems get much more challenging when you have more than 3 colors. Suppose you have 32 colors, you have to divide this area into 32 different colors. You can imagine the rest of that. Another approach to compensate for this resolution issue and other issue is to use scanning-based methods. So in push-brooming scanning, for example, it captures spectral content along one spatial axis, and then you scan through the other spatial axis to capture the entire data cube. And in the other approach, quite similar, but optically or from physical perspective could be very different, is you capture spatial image at a specific wavelength, and then you scan through the wavelengths to capture the entire data cube. Of course, these scanning-based approaches require scanning, so you have temporal inconsistency called motion artifacts rather than spatial inconsistency. Well, of course, an alternative approach that compensates for these problems is to use a tomographic snapshot approach to measure multiple parallel projections of the 3D data cube. Okay, I paused a little bit because Dr. Askuti is here, and he's an expert in this field. So this, as you can see in this picture, well, this is a beautiful approach, and this is in fact a computational imaging sensors where you have to use some sort of estimation approach to this data cube back from these parallel projections. But one problem that this has is, as you see, this a lot of black areas doesn't have any signal. So you have first loss of resolution, and you may simply have low SNR as well. So in summary, the approaches that I have described has some issues more or less. In particular, color filter array approach and the tomographic snapshot approach has resolution loss, signal-to-noise ratio degradation, and the scanning-based methods are suffering from temporal inconsistency called motion artifacts. Our group has attempted to sort of resolve all these issues at the same time by implementing a snapshot coded aperture spectrometer. In this system, a 3D data cube representing the scene is imaged onto the aperture code by objective lens, and then that aperture code spatially modulates the data cube at each spectral channel, and then that modulated data cube is sheared by this optical, the combination of optical elements, which is then integrates along the spectral axis to produce this coded projection measurements. This, in general, this problem forms an underdetermined system of equation problem because the number of measurements is always smaller than the number of elements in the data cube. So we applied compressive sensing idea to resolve this issue. And especially we used total variation minimization method. We used the total variation minimization method because natural scenes are not sparse in the canonical basis, but they tend to be sparse in the gradient or variational domain. For example, these images have so many non-zero elements in this domain, but if you take a gradient, if you take some finite difference, then your gradient image will be sparse. So to test this concept and to demonstrate the concept using our system and using the total variation minimization method, we image this scene consisting of some plastic objects. And then we apply and we process the total variation minimization method to this 2D coded projection measurements to produce this 3D data cube information, which shows the spatial content of the scene from 455 nanometers to 650 nanometers. So as you can see, the content are very sparse. A lot of spatial images contain actually most zeros. So to understand how this coded measurement may efficiently encode the 3D data cube information into the coded projection measurement, it is worth analyzing the problem from Fourier domain perspective using Fourier projection slice theorem. How many of you know about Fourier projection slice theorem? Tomography? Okay, well, good. Fourier projection slice theorem tells us that a parallel projection, which means summing along all these parallel lines of your signal. So if you have a parallel projection in the spatial domain, then that corresponds to a slice through the Fourier transform of this signal in the spatial domain. So as you can see, this slide is obtained by taking this parallel projection. This is important because our sensing process begins with taking convolution between the Fourier transform of the scene data cube and the Fourier transform of the random code data cube. So when they take a convolution, this code data cube, Fourier transform of the code data cube tries to mix up and spread the information all over the place rather uniformly. And then the 2D coded projection can be understood as a slice of this data cube using Fourier projection slice theorem. So in comparison of the case without using the coding concept, if you use coded data cube to take this convolution, as I mentioned, this convolution tries to spread the Fourier transform information to all over the place. So no matter what slice you take, they rather contain roughly enough amount of information. So if you don't know anything about the signal, that's roughly the optimal way of getting signal. On the other hand, if you don't use coding, then your Fourier transform of the data cube has some structure such that if you take a slice and if you really get unlucky, then you get so little amount of information of the Fourier transform. Recently, we have moved on from spectral imaging with spectrally sparse sources like fluorescent light sources to spectral imaging with more broadband sources such as white light sources. This problem is important because the spectral contents are no longer sparse, so you may not be able to use just one measurement to obtain the accurate reconstruction. So our approach to compensate for that is to translating the aperture code and take multiple snapshot measurements. To demonstrate the concept of multi-frame acquisition, we image this scene of a leaf, and from a snapshot, this is what we obtain using our total variation minimization method, which is full of the estimation artifacts. And this is what you obtain with multi-frame acquisition. Comparing the two, you can see the substantial improvement in the accuracy of the reconstructed data cube. To obtain more quantitative analysis, we image this scene and also measure the reference spectra using ocean optics spectrometer. And this figure compares the reference spectra with those taken at the same spatial locations using our system. And this is the data cube estimation obtained using our system from a single snapshot. And then this is again using multi-frame acquisition method. So again, you can see the substantial improvement in the accuracy of the spatial content of the data cube. So this system demonstrates how physical coding and multiplexing can be used to implement compressive sensing idea and to solve the underdetermined system of equation and eventually solve or resolve to some degree some of these issues simultaneously. In summary, we have seen how signal processing concepts can be integrated directly into the design of physical system, which has implications on solving practical challenges and eventually have real impact on real-world applications. So this is formal end of my formal presentation, but I'd like to take many questions as possible. Just for your interest, this is another thing I may want to talk about if I'm invited again. This is interferometric imaging using compressive sensing. So just to keep you interested, I'm not going to reveal anything on this. Yeah, thank you very much. Yep.
Questions?
Yeah.
Yeah.
When you were talking about taking the multiple snapshots using a piezo actuator, I guess, to move that aperture code, what kind of frequency are you taking those snapshots?
How fast it's moving?
Right. Yeah.
Right now, we are taking like 4 frames in tens of milliseconds. Yeah.
So how does that compare to some of the approaches that you were talking about that suffered from the temporal disturbances? Because that does introduce a little bit of that as well, right?
Yeah, true. we eventually anticipate that if we can use DMD array that has very high frequency in moving, then we can actually synthesize a lot of different patterns at the same time. We can have many measurements over a short time. So that'll eventually solve some of the issues. But yeah, of course, multi-frame acquisition can suffer from some of the temporal artifacts issue too. Sure. Yeah, that was a very good question. Thanks. Yes.
Thank you, Dr. Choi. I know that in my own work, one of the hardest issues relates to resolution in the spectral domain and the spatial domain, and eventually in other domains as well. But could you comment on, and the challenges there that I often see is comparing different approaches to look at the different resolutions that they might offer. But could you comment on that in general, and also on how the coded aperture itself might affect resolution in the spectral domain, for example, as well as in the spatial domain?
My perspective is that so for a given detector array, you may not be able to make measurements that can give you perfect resolution that you want. So the question is how to make the optimal optimally informative measurements. So that's why we took the coded aperture approach. I think I actually thought about and read your paper, thought about the problem, and what I'm guessing is that we can combine the tomographic approach with the coded aperture approach and maybe significantly reduce the number of projections that is currently required. And then that'll, in fact, affect the resolution improvement a lot. Yeah. Of course, but yeah, you need smart algorithm and have to think about how we have to combine that into your system. Yeah. Thanks. Thanks for the nice question. Yes.
How does this type of system degrade with the addition of noise? So, one of your assumptions is that you're getting a nice matrix, and then the amount of noise that I guess what I think is that I could see the noise effectively affecting the sparseness. The noise is maybe some other type of sparse information that's being added into the this whole set of computations.
Yes.
So
yeah.
how robust is this system?
That's a very good question. In fact, the reason we use coded aperture from physical perspective is if you think about slit-based method, then it can only obtain very small amount of light. But coded aperture can let through a lot of photons. So regardless of the mathematical interpretation, we actually get more photons by using coded aperture. So we have high signal-to-noise ratio. Yeah. But if you have very bad SNR, then your estimate can be well affected by that low SNR. Yeah. Thanks. Yes.
I'm not familiar with any of this, so I'm curious about your coded aperture. How is it physically made, and is there constraints on the size of how big or how small it can be made?
That's a very good question. Actually, my background is signal processing, although I work with a lot of physicists. One thing I know is we order those coded apertures from a company, and I try to get, for some of my interests, I try to get nanoscale coded aperture, and they rejected the, they declined the order. So I'm guessing, I know we could make that in a micron scale very accurately, but in nanoscale, it's probably very tough, and I think a lot of nanoscience is devoted to making nanostructure in a very high accuracy. So does that answer your question?
Yeah. Well, so on the big size, is there an advantage to having a much larger aperture? You would
Yeah. You can easily make a very large aperture.
Okay.
Yes. Yeah. Any?
Yeah, I have a question.
Yes.
So in terms of computations here, what are we talking? What kind of time scale are we talking about here?
So I didn't actually specifically talk about that. So it depends on what type of algorithms you use. Right now, what you use is called the twist algorithm. It's just basically combined thresholding and scaling of the signal, as you might know well. It's coming from the best basis selection approach. In fact, for optical imaging, your matrix is couple million or even probably larger than like couple million by couple million. We can process that data. If we use GPU, then couple seconds. And if you don't use GPU, just regular computer with just a little bit larger memory, then it's currently taking 20 minutes. So it depends on how you process the data. But that's a definitely very important question and something that I have to look into. Yeah. We're currently trying to make that real time. Yeah.
That's what I thought you would, yeah.
Yes. Yeah. And it's rapidly growing field. So like every day when you wake up, there are like more algorithms. Yeah. But there's no one around me like, you know, if it's really fast or slow. So I have to read all those papers and students come in, come on, leave me alone. Yeah. Yes.
How are the code sequences used in the aperture design?
Pardon me?
How are the code sequences used in the aperture
Code
design?
sequence?
Isn't it a kind of a mask?
Yes, yeah, it's a mask.
So how is that mask designed? What principle?
So if you remember, like what I talked about in the background is the random matrices is known to satisfy restricted isometric property. So we intentionally designed that using a quasi-random pattern. Yes.
Now, is the structure of that pattern related to the complexity of reconstructing the image afterwards?
That's a very important question. Not in the current way, but if we use that structure, I think we can make it faster. Thanks for the important point. Yeah, yeah. But currently, it's not used in the reconstruction algorithm. Yeah. You asked the question already, right?
I'm going to have at least one more chance. Related to the sparse matrix, and what you spoke about is really helpful to my ears. But still, it doesn't avoid, it seems to me, the challenge of calibrating that matrix, even if it is sparse. Could you comment on the best practice to calibrate that? I mean, because in theory, it seems like what you would want to be able to do is have essentially a multidimensional impulse function,
yeah,
right? And then
that's
scan
true.
through all of your dimensions. But that's practically impossible. So what's the practical way to calibrate?
For the optical imaging, I was actually thinking of using some sort of adaptive optics and sort of monitoring, you know, what's coming out of the system when you change that specific like aperture code pattern, for example. But I'm not sure, you know, how much it can help in practice because I've never had a chance to put that forward in our lab. Yeah. So
So your current results are based on basically a analytic definition of your inputs and outputs, or something else?
what, those images?
Sure. I mean, you've somehow created H, a real
Yeah,
H that you
matrix.
use.
Oh,
How do you
yeah,
populate
well,
the H matrix is sort of what I'm asking.
Oh, okay, I see. I understand your question better. So in fact, in practice, you know, when you have small aperture pattern, there's something called diffraction effect. So when you have small hole in the aperture code, it makes some blur when it comes out of the aperture code. So your model, if you use that random code aperture pattern itself, then it doesn't fit the physical model. So what we do is we take a picture of that aperture code using monochromator. But of course, that's substantial amount of work in most cases. But for our case, we carefully design the relay lens and the objective lens so that there is not much blur. So maybe if you have length 10 signal, then your blur is like 1 or 2 pixels at most with very low signal amplitude. Yeah. Thanks for the good question. Yeah.
Joel, do you want to go ahead? Sure. It would seem.
Yeah.
It would seem like, at least at a superficial level, the problem of recovering the images from observations through a sparse matrix is very similar to the decoding problem in low-density parity check.
Yes, exactly. Yeah, that's true.
And are there any fruitful connections to be made between those two problems?
Yeah, I know a lot of people have been working on that, but since it's not my field, I just know there has been many connections. So I know there's literature, but I don't know details about those.
Actually, to sort of pick up on that, Louis Scharf actually has tried to make some connections between random coding from the Shannon's random coding theorem with this. I don't know whether he published something, but there is people have thought about this, and Louis Scharf is one of the persons that I know who has done that.
One comment that I may make is that I'm not sure it's totally relevant, but one of the papers I've accidentally seen was to consider that compressive sensing problem from graphical theory perspective, and that was connected to the low density coding problem. And then if the graph satisfies some property, it's actually called the statistical restricted isometry property, then you can actually apply compressive sensing reconstruction as a decoding algorithm to that low density coding problem. That's something I know, but I'm not sure how relevant that could be. Yeah.
Sure.
Your assumption about the sparsity depends upon the particular image that you're dealing with, and then how to get a transform that would. Is there any avenue for adaptivity in the system here? Can you change something according to the data that you are collecting and say, oh, I'd rather use this aperture than that aperture somewhere in the system?
Yeah, that's a very good question. In fact, I initiated the idea of using multi-frame. So the reason was that, so one of the idea of compressive sensing is that, there has been some work that proves each measurement in the compressive sensing roughly contains the same amount of information. It's called democratic information. But on the other hand, people have used the machine learning idea to learn different bases for different class of objects. So if you have spectral imaging, of course, as you can see, there's like very high similarity, correlation between the spectral channels. So you might be able to use, if you adapt your sparsity spaces, then you could use this just very well. But in general, this is not well exploited. Or in like SAR imaging, synthetic aperture radar imaging, you have buildings and trees and things like that. So people have used computer scientific algorithm to make a better learning algorithm. And in terms of your question, I'm not sure how we should change the aperture code to adapt our system to the different signals. I guess the more important point is to use this spectral relationship rather than adapting the aperture code to the signal. Because I guess this is something that is obvious at this point. But eventually, your comment could be very valuable because no one has been considering, how we should adapt the system to the class of signals.
Your picture here has something that this kind of, okay, you got red, green, blue.
Yeah.
And so you need to go through the entire spectrum in order to pick up each one of those objects.
Yes.
But if you got no information in one of them, you could concentrate on a different spectral region without losing anything.
Yeah.
That was basic thought.
Yeah, sure. Yeah. In that case, So I guess it's highly relevant because in that case you have to know where the relevant spectra are. So it's of course adaptive, but this compressive sensing assumes that even if when you don't know where the signals are, if you just randomly sample this signal in some way, then your each measurement, without knowing where the spectra are, each measurement contains optimal amount of information you can get.
That's the assumption.
Yeah, and mathematical proof too. But you have big assumption that the object is sparse. Yeah.
Can you comment about also the 1 pixel camera as to how you can how practical and how it connects to this work?
Yes, it's actually related to Dr. Yaskuri's question. Single pixel camera is a very interesting prototype camera of compressive sensing. However, from optical perspective, first of all, it takes large amount of time, and every time you just measure a single pixel. So although each measurement measures optimal amount of information, you have to measure tremendous number of pixel elements. And as Dr. Yaskuri mentioned, I think the calibration. So the current prototype assumes that they have perfect 0, 1, 0, 1 elements. So that won't be ever true in practice. Yeah. So it's an interesting prototype camera, but it has a lot to improve. Yeah. And another thing I have investigated is, so in this, like in all those matrices that satisfy restricted isometry property, that assumes you can have both, positive and negative values. But in practice, you can only measure, in optical imaging, you can only measure positive numbers. Then, your space for the signal to reside in is highly limited. It's non-negative orthont. So your system could be highly ill-conditioned, regardless of their assumption. So I guess what they do is they take 2 measurements for the single thing and synthesize the measurement. But it's, again, the point is to compress the signal, but they have to make twice more measurements. Yeah. But I love that idea. It may advance, some of the fields. So I'm not particularly negative about anything in the world.
Any other questions? Well, if not, let's thank our speaker again.
Thank you very much again.